Talk about work. Um, we want to be able to calculate the work done by using the force, whereby the work, according to physics, work is equal to the force times the distance by which that work has intervened or traveled. The definition for work done by a constant force is just the work is said to be the force of the object with respect to the distance um, that object has covered. This is in terms of constant force. So obviously, there would be in this situation calculus would not be needed. But if it's a variable force, that means that over the progression of time, things are changing if the distance is not constant. So if an object is moved along a straight path by continuously varying force f of x, then the work that is done by the force as the object is moved from x equal to a to x equal to b is given by, this is the work, the limit with respect to the partition shrinking close, tending to zero, of the summation of the change in the work. Where here, that's no more than the integral from a to b of the function of the force of the function, capital F of x dx. Now in the last section, I made note of Christian Huygens, and I went back and listened to my video, and I sound kind of weird by noting the aspirations of man. So I thought I would note this young lady here. Now check this out. This is 1706, 1749, and she didn't live that long, bless her heart. So she died in her 40s, 43, 42. A very pretty young lady, and she contributed much to the study of mathematics. There you can see the caption in the book that she translated a lot of Newton's work into French. And then she had some books of her own that she wrote, and she was instrumental, her, along with others, Newton, there, Descartes, Rene Descartes, the great French mathematician and philosopher and theologue. I must note that as well. And others, Linus, Hooke. We'll talk a little bit about Robert Hooke and Hooke's law today. Excuse me. But she was a rarity and very beautiful. I think she would do well to kind of cover up there. That's what my grandmama would say. You know, you going out like that, you got to watch yourself. Anyway, let's get back to the mathematics. This page is not. I want you to be able to see it. There are three particular laws that deals with force that we want to consider in physics and calculus. Hooke's law is one, that the force is said to be computed with respect to the distance of the stretch or the distance of the compression if it's a spring, and Hooke was dealing with the pendulum of not the pendulum, excuse me, I'm thinking about something else. Hooke was dealing with a spring that's being compressed or is being extracted and trying to calculate the force from that spring by using the spring constant K. We call that the constant of proportionality. So we get force that way according to Newton's second law. We're able to also calculate the law of we were able to calculate the force based on gravitational pull from two particular masses. Um, then Coulomb's law. So I think it best that we consider the problems here. I want to note that we did make mention of the integral that we would use to compute the work. So here the work is equal to the force, the integral of the force with respect to the change in x dx. And that's pretty much all you need. There's something else we can consider as we get to it. Look at this problem here. Use Hooke's law to determine the variable force in the spring problem. And so we have a force of 5 pounds compresses a 15-inch spring a total of 3 inches. So from there, by using Hooke's law, we have the force is equal to the spring constant times d, the distance of the scratch. Here is being scratched 3 inches. The force is equal to 5. So we say here this implies that 5 is equal to 3 times k. So the spring constant 5/3. So now calculate the work. The work here is the integral. How much work is done in compressing the spring 7 inches? So from 0 to 7. The force, what is that? The force is equal to 5/3 times x. So work is the integral of the force times dx. So 5/3 x dx. And here we have 5/3 x squared divided by 2. That's evaluated from 0 to 7. And so we have 5/6 times x evaluated at 7 is 49. And here we have inches, pounds. And I did the math. I thought I did. So 245/6. Inches, pound, inches, pound. The next one, a force of 20 pounds scratches a spring 9 inches in an exercise machine. So there they want us to compute the constant of proportionality, or the spring constant. So we have the force is equal to k times the distance of the scratch. That is 20 pounds. You know, pounds being a force is also weight. So force is equal to weight. So here we have 20 is equal to 9 inches times k. That implies that the spring constant is 20/9, with the force being 20/9 times x, the distance. So the work is equal to the integral. Find the work done in scratching the spring 1 foot. So from 0 to 1 of the force, 20/9 x dx. So here we get 20/9 times x squared divided by 2. So that gives us 10/9 x squared. And that's evaluated from 0 to, this is 1 foot, but the 9 inches, so I need to put the units together. So it's going to be 12 inches. So 0 to 12. Thought something was odd. So So we have 10 over 9 times 12 to be squared inches foot. And we can simplify that. So the work is 10 over 9 times 12 times 12. And so the 12 is 3 times 4, then times 3 times 4. So it looks like 160 inches pounds, and if we're going to convert that to foot pounds, so this will be times 1 foot over 12 inches. So it's 40 over 3. Foot pounds. Now, the next problem, here pumping water, a rectangular tank with a base of 4 feet by 5 feet and a height of 4 feet is full of water. The water weighs 62.4 pounds per cubic foot. That's the weight density of water, how much work is done in emptying water out over the top edge in order to empty part A, half of the tank, and then part B, all of the tank. Well, the base is set constant, but this height is changing because water is going in. So this height is 4 minus, it's up and down 4 minus y. We can use the volume to calculate the work. So here, force would be equal to the weight density of the liquid times the volume. So the weight density here is 62.4. And so this is pounds per cubic feet. And then the volume is going to be 5 feet times 4 feet times that height, which is changing. So it's variable, right? So that's what that means. So this is 5 feet times 4 feet times 4 minus y feet. Okay. So on your calculator, we calculate the 62.4 times 20. And that gives us 1,248. 1,248, and then this is times 4 minus y. Well, that just gives us pounds. Well, what does the foot pounds come in terms of what the weight is equal to. But this here gives us the force, and then the distance is calculated by the dx. So part A, we have the integral. You want to fill half the tank, so you're going from 2 to 4. And so we have the weight density times the volume. This is 1,248 times 4 minus y dx. So we calculate that. So 1,248 times 4y minus y squared over 2. These terms are being calculated from 2 to 4. And so the work, 1,248. Here we get 16 minus 8, then minus 1,248. We evaluate at 2, so we get 8 minus 2. And this is 1,248. This is 8 minus 6. 8 minus 6, which is 2. We get 2,496. And this is in foot-pounds. Now part B, we're going to calculate filling the whole tank. So the work, we got most of the work already done. Hey, it's a double statement. We go from 0 to 4 of this same formula. 1,248, 4 minus y dy. And so this comes out to be the 1,248 4y minus y squared over 2. Evaluate that from 0 to 4. And all we need there is the 1,248 times the 16 minus 8. That's what that is. 1,248 times 8. It gives us 9,984. Foot-pounds. Thank you.